Hi, good morning, guys. Welcome to my project presentation. In my project, I'm going to explore a dynamic solution algorithm to optimize the hash conditions. Remember during the lectures, we discussed the hash table data structure and some algorithm like Kuka hashing, which could support the search as the need in big of one worst case time and big of one insert expected time. Actually, although the Kuka hashing strategy, when we apply like multiple hash functions or proper hash functions, could avoid some excessive concentrations of conditions to a certain extent. But I think they're still too basic and not practical, especially dealing with a huge data. So in my project, I will explore a more advanced algorithm using dynamic hash tables and a set of different unidentified hash functions to minimize conditions to some acceptable degree. Here are some. So let's talk about some definitions about the algorithm. The definition one is about the condition depth. So for a set of data D and the S item in the hash table. Di is cardinality where for all key belongs to D, the map function Fk is equal to Hi, which means they map to the same direction, same position in the hash table. So we remember the number of conditions. So the bigger Di means the more conditions in the corresponding index in the hash table. And also it results in more time cost to search the items or insert the items. For definition two, the acceptable condition depth. So for a set of data D and the size of the hash table S, we record the average acceptable condition depth as D average equal to D divide S. After inserting all data D into the hash table, we record the lowest condition depth as D min. Therefore, we define acceptable condition depth as D is smaller or equal to 2 times D average minus D min. So the definition three is the excessive condition depth, just the opposite to the acceptable condition depth when it's greater than 2 times D average minus D min. We defined it as the excessive condition depth. So now let's talk about our algorithm using examples. Assume now we have a set of data D equal to D1, D2, D3, etc. And we create an empty hash table and mark all index as zero, like I showed in the right side. So now we have to set a threshold T. For example, 3. Actually, T is based on the definition 2 and the definition 3 in the last slide, which is the acceptable condition depth and the excessive condition depth. So to simplify our examples, we just use 3. And we also need to set the ratio factors R. Remember that R have to bigger than 0 and smaller than 1. So for our examples, we set is 0.5. We will talk about the use of T and R in the following slides. So now let's talk about how to construct our data structure. So assume now we insert the data into the hash table, which we have D1, D2, D3, D4, and D5, and D6. So now this is our empty hash table T1. We assume that T1 and T3 is mapped to the indexed one of the hash table. So it's D1 and D3. Now we have two data mapped to the same index. So we change the 0 to 2 and record it in our hash table. And for the D4, we mapped it into the index 3. So now we have one data here. We mark it as a 1. For D2 and D5 and D6, assume we map to the index 4. Now we have 3 data here. So we change the value to 3 in this index. Assume now we need to insert D7 into our hash table D1. Assume that we insert the D7 is mapped to the index 4 in our T1 table. Here we have T2, T5, T6, T7 now. So remember we said our threshold T is equal to 3. And so now we cannot insert into this corresponding location because this changes the value to 4. And it's exceeded our threshold. So now we need to construct another hash table T2. And remember that we said our ratio factors R is equal to 0.5. So now our the size of our T2 is equal to 8 times 0.5 is equal to 4. So next we did in T1, we have a set of 4 hash table and we mark every index as a 0. So now let's handle this not accept cognition dips. So remember we have 4 atoms in the index 4 in T1, which is not acceptable. So we construct the T2, and so we insert the chains of these values into the T2. Here we have D2 and D5 here, and the D6 and D7 here. So we have 2 atoms here. We set the 0 to 2, and we also have 2 items in index 1. We set the values to 2, and also we need to set the corresponding index in T1 as -1. This is the flag. It's very important. We have to set it. So for the next slide, assume we need to insert D8 and D9, and they also corresponding to T1 in index 4. Actually, now we find that the index 4, which D8 and D9 mapped to, this flag is -1. So we cannot insert here. We go directly into D2. So we insert D8 and D9 in index 0 and the index 1. So now we have 3 items in index 0 and 3 items in index 1 in T2. So we change the value to 3 and 3. So in next slide, assume we need to insert another data D10 into our hash table. Assume that it's still mapped to the to index 4 because we want to talk about the extreme case. So now we cannot insert into T1. So we go directly into T2. Assume that D10 is mapped to the index 1 of T2. Now, we cannot insert it here because we now have 4 items in index 1. So we have to construct a T3. Recursively doing that as we did for T1 and T2. So now we have T3. Remember in T2, we have 4 items in index 1. Now we cannot have it now because it's not acceptable. So we change the index 1 into value as -1 as our flag. We insert D6, D7, and D9 in D10 in index 0 and index 1 of T3. Remember the ratio factor is 2, so we have a size of 2 here. So this is the basic idea of the recursive strategy of my algorithm. When we need to insert the data D into our hash table, we first need to check in T1 in its corresponding index. If it's not -1, we just insert into its corresponding index directly. If it's -1, oh, we need to go to the next level. And we check the next level as same as the first level. If it's -1, we need to go to deeper level. And we just check all the levels in order until we reach the bottom level. If in any of the level within our existing levels it works, so we insert it directly. If it's not works until the bottom level, we may have to increase our level by 1 and then mark the corresponding index as -1 and insert all the data in the chain into the next level. So it's just the recursive algorithms. And of course, it's very basic ideas, and I'm still trying to figure out the time complexity and other like mapping functions is still very important for my algorithm. I think that's a basic idea of my algorithms. Thank you very much. Have a good day.